Welcome back to The Explainer. Today we're actually diving into a biography, but not of a person. We're looking at the epic, billions of years long life story of a star. Think about it. Every single atom in your body was likely forged in the heart of one of these celestial giants. So, today we're going to explore the mechanics behind how these brilliant points of light are born, how they survive, and ultimately, how they die. I mean, have you ever looked up at the night sky and just wondered, how exactly does a star die? It's a fascinating question, right? Because much like us, stars aren't eternal. They have a very definite life cycle. They're born, they live out these incredibly dramatic, fiery lives, and eventually they face their own kind of cosmic mortality. But to truly grasp their death, we first have to understand the intense mechanics keeping them alive. So, this entire journey is governed by a concept known as stellar evolution. Basically, this is the complete life cycle of a star, encompassing its birth, its long life, and its eventual and sometimes totally explosive death. It's this epic chronological narrative driven purely by the laws of thermal physics and gravity. A star isn't just a static object hanging there. It's a wildly dynamic, evolving entity. Okay, let's dive right into it. Here's our roadmap for this explainer. First up, the cosmic birth. Then, we'll look at the forces at war. Third, what happens when it's running out of fuel? And finally, the two ultimate fates, low-mass stars becoming white dwarfs and high-mass stars becoming black holes. Let's get going. All right, Section 1, the cosmic birth. Before we get completely bogged down in the atomic mechanics, we really need to grasp the massive chronological scale we're dealing with here. At year zero, we have a nebula, just a vast drifting cloud of dust and gas. Fast forward millions of years, and gravity works on this cloud to form a contracting protostar. And finally, after billions of years, it enters the main sequence phase, becoming a stable, fully formed star. So, how exactly does that initial spark of life happen? Well, every star starts as a nebula. This is a massive cosmic cloud made up of about 99% gas, mostly hydrogen and helium, and just about 1% cosmic dust. What happens next comes down to that fundamental law of physics, gravity. Gravity slowly but relentlessly starts pulling all those scattered gas particles inward. As these molecules get crammed closer and closer together, they start colliding like bumper cars. Their kinetic energy just surges, which causes the density and the temperature to absolutely skyrocket. This immense heat and pressure eventually forge a protostar, which is basically a super dense baby star just waiting for that final spark. And once that protostar gets hot enough, it steps into adulthood. Which brings us to Section 2, the forces at war. To literally just stay alive, every single star has to wage a delicate billion-year cosmic battle. On one side, you have the inward force, gravity. Gravity is completely relentless. It's constantly pulling all that mass inward, trying its absolute hardest to crush and collapse the star. But on the opposing side, you have the outward force, internal pressure. This is the immense gas pressure generated from deep within the star's scorching core, pushing back outward against that crushing gravity. When these two warring forces reach a perfect stalemate, the star achieves something really profound, a state called hydrostatic equilibrium. This is the perfect, stable balance where the inward gravitational pull exactly equals the outward gas pressure. As long as the star can maintain this equilibrium, it won't collapse in on itself and it won't blow itself apart either. It remains perfectly stable in the absolute prime of its life, that main sequence stage we mentioned earlier. But you might be wondering, what exactly generates all that outward pressure? The answer is nuclear fusion. Deep down in the core, the temperature is just unimaginably high. First, the star violently smashes hydrogen atoms together to create helium. That's the primary engine, and it releases a massive amount of energy, literally the heat and light that makes a star shine. Later on, if the core gets hotter, that helium fuses into carbon and oxygen. And if the star is massive enough, it can keep fusing heavier and heavier elements, all the way up to iron. This fusion engine is, quite literally, the heartbeat of the star. But a star can't burn forever, right? It only has a finite amount of hydrogen in that core. So let's move to our critical turning point. Section 3, running out of fuel. That delicate balance we just talked about, it totally shatters when the hydrogen fuel runs out. It triggers this fascinating, almost catastrophic chain reaction. Without hydrogen, nuclear fusion slows way down. And because fusion slows, that vital outward gas pressure drops. Suddenly, gravity takes over and starts winning the war. The core gets violently crushed inward and contracts, which paradoxically heats it up even more. Meanwhile, the outer layers of the star actually lose their gravitational grip and expand rapidly out into space. The star swells up to a massive size. Now, what's really interesting here is that at this exact moment, the star's initial mass, like how big that baby cloud of gas was to begin with, completely dictates its destiny from this point on. If it's a low or medium mass star, the outer layers expand and cool off, and it becomes a red giant. But if it's a high mass star, we're talking a true cosmic heavyweight, it undergoes an extreme expansion and becomes a red supergiant. Inside that massive core, the pressure is so intense it can fuse those heavier elements like silicon and iron. Let's follow that first path to see how the smaller guys end their journey. Section 4, low mass stars and white dwarfs. For a low or medium mass star, the end is actually relatively peaceful. As a red giant expands, those outer gas layers just beautifully drift away into space, creating this massive, glowing cloud that astronomers call a planetary nebula. And what's left behind in the very center? Just the naked, exposed core. This is the white dwarf. To put that into perspective, it's roughly the size of Earth, but it weighs as much as our sun. It is mind-bogglingly dense. There's no nuclear fusion happening anymore. It's simply a glowing hot ember, just slowly cooling down over billions of years in the dark of space. But what if the star is massive? Well, the physics here get pretty explosive. Section 5, high-mass stars and black holes. Contrasting these two paths really reveals the sheer power of gravity. While a low-mass star ends quietly as a white dwarf, a massive star becomes a red supergiant. And when its core fills up with iron, that is a literal death sentence. Fusion halts in a fraction of a second. Gravity crushes the massive star inward so fast and so hard that it rebounds in one of the most powerful explosions in the entire universe, a supernova. Out of the absolute chaotic destruction of that supernova explosion, one of two extreme objects is born. If the remaining core is heavy, it leaves behind a neutron star. This is the collapsed core squeezed so tightly that it becomes insanely dense. They often rotate incredibly fast, beaming out radiation, which is why we sometimes call them pulsars. Or, if the star was truly colossal, the core completely collapses under its own gravity to form a black hole. A black hole is a region where the gravitational pull is so unfathomably strong that it physically bends space-time. Not even light, which travels at 300 million meters per second, can escape its grasp. It's literally a point of no return. Now, these are vast, almost terrifying cosmic concepts, but let's ground this for a second and bring it back home. The big question is, what is the ultimate fate of our own sun? Which of these two paths is it going to take? Well, our sun is a medium mass star. Right now, it's perfectly balanced in that hydrostatic equilibrium we discussed. It's sitting comfortably in the stable main sequence stage, producing energy by fusing hydrogen into helium. And it's been doing exactly that for about 4.6 billion years. But in about 5 billion years, its hydrogen fuel is going to run low. It'll expand into a massive red giant before eventually shedding its outer layers and fading away as a quiet, dense white dwarf. But here's a thought to leave you with. What happens when that white dwarf eventually loses all of its heat and goes completely dark, trillions of years from now? Are we looking at a future universe filled entirely with invisible dead stars? Thanks for joining me on this explainer. Keep learning and keep looking up.